The CAP theorem is one of the most important theoretical results in the past 2 decades. When we look at the 3 main properties of distributed systems, consistency means to keep the data up to date and avoid conflicting views of data. Availability means the degree to which the system is reachable to perform work, which in the end leads to updates on the data. And finally, partition resilience, the robustness in the event that we have a partition of the network and temporarily lose the ability to communicate between the nodes. The CAP theorem, originally brought up by Eric Brewer from UC Berkeley as a simple conjecture, says that in a distributed system you can only have 2 out of these 3 properties. And this theorem has been proven by Gilbert and Lynch. Now, in the modern interpretation, we no longer consider 2 out of 3. It's more you have to pick your poison. Which of these 3 are you willing to compromise on? So you have to allow for some degradation or corner cases because you will never have all 3 100% at the same time. In order to illustrate what this means, I like to use this data structure here, a DHT or distributed hash table. It works like a regular hash table in that it stores data by the hash of the key. It does so using multiple nodes, and every node is responsible for a part of the range of the hash function. Now, a popular implementation of this concept uses a ring topology. The nodes have a finger table because these systems can be large. And by storing links to the nodes in steps of powers of 2, you limit how many other nodes every node needs to know, while you can still reach every node within a useful number of hops. So, what does this system do for availability? Well, the data is replicated between nodes to create redundancy. So when a node fails, there should be another node that is able to restore the content. And of course, in such an event, the data is rebalanced between the nodes and the ring is closed again. So this data structure is self-healing. For consistency, well, we have a single primary copy of the data, which is consistent by default. The secondary replication protocol needs to ensure consistency, so there is still a bit of black magic under the hood, but the data structure is consistent. Now comes partition resilience, and because of the CAP theorem, we know that there must be a problem here. So let's look at what happens when we have a partition of the network. Let's assume that we cut the network pretty much in half, because the central router fails. Now what happens is that the remaining nodes try to self-repair and close the ring, and they will restore all the data that they can get from the secondary replicas in their partition. The problem is, this happens in both partitions. So we now have 2 rings. And from now on, the 2 rings will each other happily live on, even when the network partition is restored, because they don't know that there is a second ring out there. And that is problematic because each ring now alters its own state and the data diverges. So even if you would force the 2 rings to reconnect to each other, they now have seen conflicting updates. This is also known as the split brain problem, all caused by network partition. So in this sense, we have perfect availability and consistency, but because of this, we have a problem with network partitions that the system cannot overcome alone.